Hello everybody, welcome to ACE online platform. So welcome to ACE Engineering Academy. The ACE Engineering Academy is providing the online coaching for almost all engineering students for almost all the competitive exams. So it may be GATE or engineering services, GENCO, Transco or Discoms, whatever it may be. So it is providing the online coaching as well as the offline coaching for all the competitive exams. So coming to here, myself Prasad Megavarna. So I'm here to discuss the power systems. So I'm saying here, welcome to the world of power systems. So in power systems, we are going to learn about the generation of electrical energy, transmission and distribution of electrical energy, and power system analysis, and switchgear and protection, and finally, for some of the state government exams, so we are having the utilization of electrical energy as well. Right? Now, coming to in this class, we are going to discuss about the transmission and distribution of the electrical energy. Right? So we are going to start the transmission and distribution of electrical energy. In the transmission and distribution of electrical energy, so these are the concepts we have to cover. Right? So coming to this one, in this, the first chapter deals with the electrical design of the transmission line. So the electrical design of the transmission system is nothing but designing of the insulating system as well as the conductor system. So we have to design the insulators as well as the conductors. So what are the type of the conductors we have to discuss in the first chapter. So that may be solid conductor, or it may be so all homogeneous conductor or composite conductor. So about all those conductors, so we have to discuss in the chapter 1. And coming to the next one, elements of the transmission line are nothing but the RLC parameters, RLCG parameters, resistance, inductance, capacitance, and the shunt conductance. So are the parameters we are having in the second chapter. And in the third chapter, the steady state performance. So in the steady state performance analysis of the transmission line, so we are going to calculate the percentage efficiency and the percentage voltage regulation of the transmission line for different types of the models of the transmission line. The different types of the models are nothing but the short transmission line model, or the medium transmission line model, or the long transmission line model. The long transmission line model is the exact representation of the transmission line, but for our easy representation, we are going for short transmission line as well as the medium transmission line model representations. So in medium transmission line model representation, we are having different categories again: the source capacitor model, load capacitor model, and the middle capacitor model, and the two-sided capacitor model. The middle capacitor model, we are calling it as the nominal T model, and the two-sided capacitor model, we are calling it as the nominal pi model. So these are the different representations of the transmission line. For all the types of the transmission lines, we are going to calculate the percentage efficiency and the percentage voltage regulation. Those are the performance indices of the transmission line. Now, along with that one, we will discuss some more extra concepts about the surge impedance, characteristic impedance, surge impedance loading, right? So these are the concepts that we have to discuss in the third chapter. And in the fourth chapter, the transient analysis. So whenever we are having the different disturbances, so for all the disturbances, how the voltage and current waves are traveling in the transmission line, so we are going to discuss in the fourth chapter. And coming to the fifth one, voltage control and the power factor correction, the one of the major important part of the transmission and distribution. So what are the voltage control methods, what are the voltage control devices, and how to correct the power factor, we have to discuss in the chapter 5. So while correcting the power factor or while improving the voltage, so we have to correct the reactive power also. We have to compensate the reactive power also. Clear? So that in the fifth chapter, we are going to discuss about the reactive power compensation as well. Clear? And coming to the next one, about we have to study along with the overhead transmission lines, we have to study about the underground cables, so which are more safe. And in the next chapter, we have to study about the overhead line insulators. What are the pin type of insulators, suspension type, string type, strain type, about all those things we have to study in the seventh chapter. And about corona formation, so electrical corona formation we have to see. So what are the factors affecting corona in the seventh chapter. And finally, how to distribute the electrical energy. So what are the modes, right? So based on the supply AC distribution as well as DC distribution. And The methods of distribution are nothing but radial, ring main and interconnected distribution. All these things we have to study in the 9th chapter. So these are the different chapters we are having in the transmission and distribution. See here, in complete power systems, we are having different parts. So power system analysis is separate part, transmission and distribution is separate part. So if you compare the marks weightage of these parts, so they are having equal weightages. Suppose if you are having, just see here, just look at here. These are the weightage of the power system in the different competitive exams for different states. So in AP and Telangana states, approximately we are having, just here, so here we are having 22, 21, 18, 22, 29, 20. 22. So it will be EPDCL, SPDCL, Transco, right? So Telangana State SPDCL, Transco, GENCO, for different exams we are having approximately 25%. So in 100 marks we are having 25% of the marks we have to get, right? And along with that one, if you see here, Transco, so that means Maharashtra Transco and GENCO, we are having 25% of the weightage from power systems, from only power systems. Clear? And coming to the KPTC, they are having equal weightage for all the subjects. So approximately 8 to 10 marks for all the subjects. They are having approximately 12 subjects. Each and every subject carries 8 to 10 marks. Clear? So in Mangalore Electricity Supply Company, so in only power systems, they asked 29 out of 100. See how much they are concentrating on power systems. Clear? So if you compare this weightage analysis, almost all the states are majorly concentrating on power systems. So in power systems, we have divided into several parts: generation, transmission and distribution, and analysis, protection, sometimes utilization. So in all these portions, power system analysis and transmission and distribution have the highest weightage. They are having the equal weightage also. And coming to the power system analysis, it is somewhat more mathematical part, but whereas coming to the transmission and distribution part, it is the combination of both mathematical and theory concepts. So we can expect more number of theory questions from transmission and distribution part, but whereas we can expect more mathematical questions from the power system analysis. And from coming to the generation and the protection, utilization, so we'll have complete theory questions. Clear? Now, coming to the textbooks, what you can prefer. So every time I'm saying these are the textbooks, the best textbooks of power systems. So William Stevenson, right? And John Wheely publications of electrical power systems, Duncan Glover electrical power system, analysis and design, and Nagrath and Kotari modern power system analysis. So these are the best textbooks. If you want to learn power systems very clearly, you can take any one textbook and start your preparation. And these two textbooks are, every time I'm saying here, so these two are particularly preferred for state government exams. So like GENCO, Transco or Discoms, right? So you can go through these two. So why? Because we are having multiple choice questions at the end of these textbooks so that we can practice more number of questions, right? Now, what to practice now? So what to practice? To practice, here we have to take previous engineering services exam questions and previous PSC questions, public sector units questions, and previous GATE 1 mark questions, and the previous state electricity board questions, right? And along with you can take staff selection commission questions, SSC JE questions, right? And PSCs, in PSCs you can take majorly ISRO questions, and previous Indian Administrative Services questions, you can take several collection of the questions to practice. Not only for power systems, so you can do the same thing for almost all the subjects. So to get more practice. Clear everyone? Now, coming to here, today we are going to take a simple concept, a simple discussion about the voltage control and the power factor correction. So within the specified time, so in this class we have to discuss something clearly about the voltage control and the power factor correction. See here, in this class, these are the modules I am going to cover here. Why voltage control is required, first of all, and what are the methods to control the voltage, and what are the voltage control devices, and what are the advantages of shunt capacitor. There are several devices we are having. So in that we will discuss only about the shunt capacitor in this class, and we will discuss some simple problems, so which are related to the state government exams. Clear? Now, first of all, the first question here it is, why voltage control is required? Why we need to control the voltage? It is the major question, and it is one of the most important question for every power system student or every electrical student. Sir, why we need to control the voltage in the power system? What happens if you are unable to control the voltage in the power system? Just see here, students. Whenever suppose the load, at the load side we are having some rated voltage conditions. They have specified some rated voltage conditions at the load side. Now, whenever the load voltage is beyond the rated voltage, whenever we are supplying a voltage which is more than the rated voltage, at that condition what happens? See here, the major component which is depending on the voltage, is the insulation whatever we have provided for the loads, or for every equipment whatever the insulation we are giving to avoid the short circuits. So it may be insulation in the motor windings, right, or the insulators in the distribution system, right, everywhere we have given the insulators. So these insulating system always depends upon the voltage level, right. So let me write the statement. The insulation level always proportional to, we can say, highest voltage level, right. Highest voltage level is the rated voltage we are giving, right. We can say the highest voltage level. So the highest voltage, by thinking it is the rated voltage, and we have designed the insulation of the system, right. Now, whenever we are providing a voltage which is more than the rated voltage, or which is more than the highest voltage what we are expecting, then what happens? The insulation of the system will be damaged. So whenever the insulation is damaged, what happens? Short circuit takes place in the system. So because of the short circuits, there will be short circuited currents, and because of the short circuit currents, so there will be heat produced, and because of the heat, and the heat will, it is a cumulative process, right? So the heat will be continuously increasing, so that it can damage this load, or it can damage the equipment whatever we are discussing here. Clear? Therefore, whenever the voltage or the operating voltage whatever we are giving, which is more than the rated voltage, we rated. So which is more than the rated voltage, then what happens? Then insulation fails. As a result, insulation fails. So whenever the insulation is failed, what happens? Short circuits takes place. And because of the short circuits, we are having short circuit currents, which are nothing but the fault currents, we can say, will flow. So because of which I square R losses, or I square R into T, heat will be produced, so that heat will be increasing, and because of which the equipment will be damaged. Clear, everyone? So these are the things what we are having in the whenever we are providing over voltage than that of the rated voltage. Now, what happens whenever you are giving low voltage? That means whenever you are giving a voltage which is less than the rated voltage, what happens? So whenever you are giving the over voltage, this is the thing what you are having, which means that we should not provide over voltage. Now, suppose what happens when you are giving the low voltage? Whenever you are giving the low voltage, I think you have seen the incandescent bulb. The incandescent bulb or 60 watt bulb we are having, so that glows dim sometimes. So because of the low voltage, is right? And the TV screen sometimes starts rolling from top to bottom without stabilizer. So if you are using a TV, so without stabilizer, so we are having a stabilizer to control the voltage. So when you don't have the stabilizer, the TV screen starts rolling from top to bottom because of the low voltage. And your ceiling fan so is unable to rotate at high speeds even though the regulator is at 5. So it is unable to rotate because of the torque of an induction motor. The torque of an induction motor is always proportional to the voltage square if you want to say particularly. Which means that almost all the loads in power system, we already discussed 96% of the loads in power system are induction machines, and these induction machines are always depending on the voltage. The torque of these induction machines depending on the voltage. So whenever the voltage is below the rated voltage, what happens? The torque of induction motor varies, so that there will be 96% load variations are there in the entire power system, so that the stability of the entire power system will be reduced. Clear? So these are the things we are having whenever you are having a low voltage. So final conclusion is, whenever you are having over voltage, load damages. Whenever we are having low voltage, load misbehaves. That means we are unable to get what we want from the load. Clear? So from the tube light or from incandescent bulb, we are unable to get the lighting. From fan, we are unable to get the wind. So these are the problems we are having with the low voltage. So that definitely the voltage should be controlled. So that the voltage should not be beyond the rated voltage and it should not be below the rated voltage. It should be exactly at the rated voltage. There may be 5 to 6% variation. 5 to 6% tolerance will be allowed to that one. So there should not be more tolerance between that one, beyond that one. Clear? Now coming to that next one, what are the voltage control methods? If you are having a large interconnected power system network, so there are several buses we are having. So we don't know where we are having the problem. We have to go to the bus and we have to check there, is there a problem or not, or the loads are misbehaving, or so that the loads are damaging, everything we have to check. Clear? Suppose whenever we are having a power system like this, so this is the generator we are having, and we are supplying the several loads like this, for example say. So here we are having one load, and here we are having one load, and here we are having one load, and here we are having several loads are connected here. So that it is load 1, load 2, load 3 and load 4. So these are the loads we are having. Now at all the loads, here the voltage is V1 and it is V2 and it is V3 and it is V4. Say for example, suppose if you got a problem of voltage at any bus V3, suppose at this bus V3 you got a voltage problem. So it may be over voltage or it may be lower voltage. So that to control the over voltage, for this generator, along with the mechanical input, we are giving the excitation. Is it right? For a synchronous generator, we are giving the excitation, so that to control the voltage at that particular bus, I am increasing the excitation of the generator. Right? We can do it. Whenever you are increasing the excitation of the generator, the terminal voltage will be increased. So whenever the terminal voltage will be increased, automatically all voltage will be changed. So increased, right? So if you want to increase the voltage, you can increase the excitation. If you want to reduce the voltage, you can reduce the excitation, right? So that this is the one of the method. What is that method? We can say it as, it is excitation control method, right? It is called as excitation control method. Excitation control method, or it is also called as internal voltage control method. Internal voltage control method. Voltage control method. Yeah. Now check here. See here, very good. Everything is perfect up to here. Whenever if you want to control the voltage here, we are controlling the excitation. But the problem what we are facing here it is, whenever you are increasing suppose if you are increasing the excitation, automatically this voltage will be increased, this voltage will be increased, this voltage will be increased, and this voltage is also increased. Right? Whenever the excitation of the generator is varied to vary the voltage at any bus, that excitation is varying all the bus voltages, which is not at all required for me. Right? I want to control the voltage at only particular bus, but whenever if you are controlling the excitation, then it is changing the voltages of all the buses. That is the problem we are facing here. Clear? Therefore, this method is not preferred to control the voltage at any particular bus. If you want to control the voltages of all the buses, you can prefer this one. But this type of problems we cannot get in power system. So all the bus voltages are having problems. We cannot face those type of problems. So that this method is not preferred. Why? It is changing the voltage of all the buses. Right? This method is changing the voltages of all the buses, which is not required. Clear? That is the problem we are facing. So that we are not preferring this method. And one more method. There is one more method is there. Suppose if you are having the same power system, suppose this is the power system we are having. This is one load, and the other load. Right? So these are the loads we are having. Load 1, load 2, load 3, and load 4. L1, L2, L3, L4. So L1, L2, L3, L4 are the loads. Now you got the problem at this bus. So this is the bus which is facing the voltage problem. Now the next method is we are going to connect a device called as voltage controlled device, VCD. So at that particular bus to control the voltage. So this is voltage controlled device. So we are connecting a voltage control device at that particular bus to control the voltage of that particular bus. Clear everyone? So remember, so this is the voltage control device, and that device is controlling the voltage of that bus only. So that this method is called as the external voltage control method. And this method is called as the external voltage control method. This is the second method, external voltage control method. Clear everyone? Now we'll take a simple power system network of a 2 bus. So then we'll see, so to control the voltage, so how to control, that means what are the things we have to follow, we have to see, right? So just take a simple power system network, right? We'll take a simple power system network here. Suppose a simple single line diagram I'm taking. So here we are having the load. Here the voltage is the receiving end voltage, which is the reference voltage I'm taking, VR at an angle of 0. And it is the sending end side, Vs at an angle of delta I'm taking. And the line is having a pure reactance, it will be JXL. And the current is flowing from bus 1 to bus 2. From sending end to the receiving end. Clear everyone? Now in this equation, if you write the current equation in the system, so what is the current we are having? So the current we are having here, it is I is equivalent to the sending end voltage minus the receiving end voltage divided by the reactance in the system. It will be Vs at an angle of delta minus Vr at an angle of 0 divided by JXL. JXL. So what is the meaning of J? Operator J always rotates the vector anti-clockwise by 90 degrees. Anti-clockwise by 90 degrees. And we are having positive angles in the anti-clockwise and negative angles in the clockwise. Therefore, this can be represented as Vs at an angle of delta minus Vr at an angle of 0 divided by XL. So the meaning of J is 1 at an angle of 90 degrees plus 90. Now, from this one, so this can be further solid as it will be Vs divided by XL. Remember, all are magnitudes only, even though if I am not representing everywhere here. So all are magnitudes and angles. Magnitudes and angles only, right? So therefore it will be at an angle of delta minus 90 minus Vr magnitude divided by XL at an angle of plus 90. At an angle of plus 90. And if you calculate the conjugate of this one, the conjugate will always give you the negative angles here. So it will be Vs divided by XL at an angle of 90 minus delta minus Vr divided by XL at an angle of minus 90. At an angle, sorry, it will be minus 90 here and it will be plus 90 here. Why? Because in the denominator plus 90 will become minus 90 here and the conjugate of that one will become plus 90. So 90 minus delta and 90. So this is the current conjugate we are having. Now from this one, we can calculate the complex power. The complex power supplied by the source we will calculate, right? Now we'll see. The complex power supplied by source, where S is equivalent to source side voltage into the current conjugate, which is nothing but source side active power plus J times of source side reactive power. That is the formula. So the complex power formula is nothing but V into I conjugate, which is nothing but P plus JQ. As we are calculating on the source side, it will be Vs into I conjugate, which is nothing but Ps plus J times of Qs. And we are having the current conjugate formula. Therefore, the complex power S is equivalent to what is the value of Vs? Vs is nothing but Vs at an angle of delta. Multiplied with the current conjugate. So this is the current conjugate we are having. So what is this one? It will be Vs divided by XL at an angle of 90 minus delta minus Vr divided by XL at an angle of 90. Clear? And from this one, if we write this one, it will be Vs square divided by XL at an angle of 90 minus delta plus delta will become 90 minus Vr divided by XL at an angle of 90 plus delta. Vr divided by XL at an angle of 90 plus delta. Clear? Now, from this equation, you can write the value of active power as well as the reactive power. So, if you want to write the active power value, you have to apply the cosine angles for both. Why? Because it is in polar form. So, if you want to convert into the rectangular form, so you have to apply cosine and sine angles. So that so when you are applying the cosine angles, you will get the active power, and whenever you are applying the sine angles, you will get the reactive power. So that for this equation, if you want to calculate the active power Ps is equivalent to Vs square divided by XL cos 90 minus Vr divided by XL cos of 90 plus delta. And what is the value of cos 90? The value of cos 90 is 0. so that the first portion will become 0. And what about cos of 90 plus delta? It will be minus sin delta. It is in the second quadrant. Cos of 90 plus delta, it is minus sin delta, and minus into minus it will become plus, so that it will be Vs Vr divided by XL into sin delta. So that you can write the active power supplied by the source. The active power supplied by the source is nothing but, therefore, PS is equivalent to Vs Vr divided by XL into sin delta. And if you write similarly, if you write reactive power, Qs is equivalent to Vs Vr divided by XL sin 90 minus Vr square divided by XL sin of 90 plus delta. So sin 90 will be 1. So it will be Vs Vr divided by XL minus Vr square divided by XL. Sorry, is it Vr square? Please check it the formula. Vs square, right? Just let me change that one. So it will be, just let me change the formula. It's not the formula we are having. So that is the receiving and reactive power formula. So at the sending end we are having Vs square divided by XL. So it will be Vs square divided by XL, sin 90 minus Vs Vr divided by XL sin 90 plus delta. So that is the formula we are having. Sin 90 will be 1. It will be Vs square divided by XL minus Vs Vr divided by XL sin 90 plus delta, it will be cos delta. Therefore, this is the reactive power equation. But what is the concept we are discussing here? The concept we are discussing here, how to control the receiving end voltage. So how to control the receiving end voltage? So that get the formula for the receiving end voltage. The receiving end voltage formula we have to write. From this equation, I am writing the receiving end voltage equation. Please check it. So you can send that part here and this part here. So it will be Vs Vr divided by XL cos delta is equivalent to Vs square divided by XL minus Qs. So when you are multiplying with XL, it will be Vs Vr cos delta is equivalent to Vs square minus Qs into XL. And from this one we can write the exact receiving end voltage equation. Vr is equivalent to one Vs will be cancelled in the first term. It will be Vs divided by cos delta minus Qs into XL divided by Vs cos delta. And remember, all are magnitudes. Now this formula is not at all that much important to remember here. What you have to remember here it is, if you want to control the receiving end voltage, you can control the sending end voltage. And cos delta value is very, very small actually for maintaining the stability of the power system. So we always prefer small value of deltas. So between sending and the receiving end, so that the cos delta value is approximately neglected in a practical power system, right? But coming to here, to control the receiving end voltage, the major component what you have to control here it is the reactive power. Right? So that controlling the voltage is nothing but the controlling the reactive power of the system. Therefore, to control the voltage, the reactive power should be controlled. The reactive power should be controlled. So that is the conclusion we got here. That is the conclusion we got here. Now, from this point, we can conclude one more thing, that the devices which we are going to connect, to control the voltage are nothing but reactive power controlled devices. Reactive power controlled devices. Clear? Therefore, the voltage controlled devices are nothing but the reactive power controlled devices. Reactive power controlled devices. So if we discuss those voltage controlled devices, the first one we can say it is the shunt capacitor. Shunt capacitor. Shunt capacitor. Second one, series capacitor. Series capacitor. Series capacitor, so controls the reactive power as well as the reactance, right? And the third one, shunt inductor or shunt reactor. Shunt inductor or shunt reactor. Fourth one, synchronous condenser, or we can write it as synchronous motor. So synchronous motor, two operations. So one is synchronous condenser operation, synchronous coil operation, right? So synchronous condenser, right? Or simply it is better to write no need here. So it will be synchronous coil or synchronous reactor, right? And the final one here it is synchronous phase modifier. Synchronous phase modifier. So all these three comes from the operation of synchronous motor. Synchronous motor. And along with this, we are having some more extra devices from the transformers. So booster transformer is also used to improve the voltage, and tap changing transformer are also used to control the voltages. Right? So in this concept we are discussing about the reactive power control devices, so that I am discussing all about this only. Clear? So along with this you can go for booster transformer as well as the tap changing transformer also. Clear? Now see here, almost all the devices whatever I have written here are the reactive power control devices or reactance control devices. Clear? Now if you see here, I am giving some conclusions at this point. The shunt capacitor is always used to improve the voltage, to increase the voltage. So almost all the capacitors, so it may be connected in series or shunt, they are going to increase the voltage. So series capacitor is also used to increase the voltage. Series capacitor is also used to increase the voltage. But if you compare series capacitor and shunt capacitor, which device is used to improve the voltage better? Which means that it will be a shunt capacitor. Shunt capacitor. Definitely we will go for the shunt capacitor. So which connection is best for improving the power factor? Definitely the shunt capacitor. But which connection is better for stability improvement? Which connection is better for stability improvement means it will be the series capacitor connection. So it will be discussed in the subject whenever we are entering into the actual subject. So everything will be discussed there. Clear up to here? So I am giving just the conclusions here. And coming to the shunt inductor, it is used to reduce the voltage, reduce the over voltages, to reduce the voltages. Actually, we are controlling the receiving end voltage, right? So the receiving end voltage we are reducing means it is having a over voltage. It is having more voltage than that of the sending end voltage. So the phenomena what we are calling it as, so the phenomena whenever the receiving end voltage is more than that of the sending end voltage, so that phenomena we are calling it as the Ferranti effect. So it may occur at no load conditions or the lightly loaded conditions. No load conditions or lightly loaded conditions. Now at that conditions, to reduce that over voltages, we are going for the shunt inductor or shunt reactor connections. shunt reactor connections. And coming to the synchronous condenser is a over-excited synchronous motor. It is a over-excited synchronous motor and it acts as a capacitor. So whenever it is acting as a capacitor, it can improve the voltage. And whereas the synchronous coil is nothing but under-excited synchronous motor. So it acts as inductor. So the inductor is used to reduce the voltage. So let me write that point also. So it acts as a capacitor and it acts as a inductor. So what is the advantage here? So in place of separate inductor and separate capacitor, we can use a simple synchronous motor. So we can over-excite that and we can under-excite that so that we can control the voltage on both sides. So whenever under voltage occurs, we can increase that one. Whenever over voltage occurs, we can reduce that one. So both we can do from this synchronous motor. And synchronous phase modifier is a separate one. So similarly like a synchronous condenser. So it is synchronous condenser always operates at no load condition, right? So overheated synchronous motor under no load condition, and here it is also under no load. But whereas coming to the synchronous phase modifier, it is also a over-excited synchronous motor with some partial load, not full load, not no load, with some small load, right? So it is over-excited synchronous motor with a small load, right? And it can act as capacitor, definitely, right? It can act as capacitor. So the difference between that capacitor and this capacitor is, so under no load condition that acts as a ideal capacitor, and under small load condition it acts as a practical capacitor. So these are the voltage controlled devices we are having in the system. Clear everyone? Now we'll discuss about the first one. So in this session, so we'll discuss about the analysis of the shunt capacitor. So what are the advantages of shunt capacitor? How it is going to improve the voltage? All those things we have to see. Now, first of all, coming to the advantages of shunt capacitor, how it is going to improve the voltage, we have to see. First of all, please check, students. Whenever the transmission line is operating, or that means whenever the load on the system is increasing, whenever you are increasing the load on the system, automatically the current supplied to the load will be increased. So whenever the current supplied to the load is increasing, so the energy which is stored in terms of current, so current is the kinetic parameter, so that the kinetic energy will be increased in the system compared to that of the potential energy. So under steady state conditions, both are exactly equal. Whenever you are increasing the load, current increases, so that kinetic energy will be increasing, and whenever you are decreasing the load, potential energy will be increasing. These two are the common phenomena we are having. Just check here. When load increases, as a result, current in the system will be increased. Whenever the current is increasing, the energy stored in the current form, it will be half Li square. Will be increased. And as a result, the energy stored in the potential form, half CV square will be reduced. Actually, energy not be destroyed, not be created. So whenever it is increasing means some of the potential energy is converting into the magnetic energy or kinetic energy. Some of the potential energy is converting into the kinetic energy. Therefore, half Li square is increasing and half CV square is decreasing. Half Li square we are calling it as electromagnetic energy, and half CV square we are calling it as electrostatic energy. Electrostatic energy. Therefore, electromagnetic energy is more than that of electrostatic energy. Electromagnetic energy is more than that of the electrostatic energy in the system. So because of this one, as half CV square is reducing, the voltage is reducing. The voltage is reducing. So as a result, we are having the receiving end voltage is less than that of the sending end voltage. So as a result, so whenever you are increasing the loading on the system, so the receiving end voltage, we are getting less than that of the sending end voltage. But one thing you have to concentrate here, it is simple electrical equations we can say, whenever you are having a voltage drop in the transmission line, automatically the receiving end voltage will be less than that of the sending end voltage. But this is the complete phenomena we can discuss here. Now, coming to here, whenever we are having the simple system like this, so here we are having the load, here we are having the load, where the load voltage we are calling it as VR1, and the source voltage I am calling it as Vs. Source voltage I am calling it as Vs. Now, the line is having a reactance of XL. What is the formula we are having? The formula we are having is to control the voltage. So this is VR is equivalent to Vs divided by cos delta minus Qs into XL divided by cos delta. So I am taking, let delta is approximately is equivalent to 0. Therefore, cos delta is approximately is equivalent to 1. Cos delta is approximately is equivalent to 1. So therefore, so we are having VR is equivalent to Vs minus Qs into XL divided by Vs is the formula. So I am taking that formula. Therefore, VR is equivalent to Vs magnitude minus Qs into XL divided by Vs. So this is the formula we are having. Clear? Now, if you see that load, the load whatever we are having, it may be combination of resistance, reactance and capacitance. We don't know what is the type of the load we have connected there, right? And because of that load only we are getting the low voltage at the receiving end. Suppose if the load is like this, suppose if the load is like this, this is the load I am taking. See here, where it is having resistance, reactance and capacitance. Capacitive reactance also it is having, right? Now for this load, as we have discussed, it is having more electromagnetic energy than that of the electrostatic energy. We are having XL is more than that of XC. XL is more than that of XC. Clear? Now, if you calculate the reactive power of the load, is nothing but, so it has to deliver or it has to absorb, both it can do. Why? Because it is having inductance as well as the capacitance. The inductor always absorbs the reactive power, the capacitor always delivers the reactive power. As we are having both the combinations, I am writing Q demand, the reactive power demand is nothing but absorbed minus delivered. Absorbed minus delivered. As it is having more inductance than that of the capacitance, the reactive power it is having Q absorbed is more than that of Q delivered, so that we are having a positive value of demand. In this system, the load having a demand of QD, the source is supplying a power of QS. Reactive powers only I am discussing here. The load requires a demand of QD, the source supplies a reactive power of QS. The only load requires this much amount of reactive power, the only source has to supply the reactive power. So that in place of QS, we can write it as QD. The total QS is exactly equivalent to QD. So therefore, QS is exactly equivalent to QD. So the source has to supply the total reactive power. We don't have an option. The source has to bear the total reactive power of demand of the load. It has to supply to the load. Clear? Therefore, just check here. The load whatever you have considered is having more reactance, inductive reactance than that of the capacitive reactance, because of which it is having more absorbing power than that of the delivering power. Clear? Therefore, we are having a positive value of reactive power. So that in place of QS, if we write QD a positive value, from 220, from VS, suppose if it is VS is 220 volts, from VS some positive value has been subtracted. So suppose if the total value, if we are getting it as 10 volts, from 220 volts minus 10 volts, we are getting 210 volts, which is less than that of the sending end voltage. So listen carefully here. As the reactive power demand is positive, some positive value has been subtracted from the sending end voltage, because of which we are getting low voltage at the receiving end. So please make that point here. Please check it. As QD is positive, some positive value is subtracted from Vs. Therefore, VR1 is less than that of Vs. So we have written the formula for VR1 only now. So you can take it as VR1. Why? Because it is VR1. Clear? Now check here. So VR1 is less than Vs. So to increase VR1, what you have to do? To increase VR1, we have to reduce the positiveness of QD. To listen carefully here. To increase the value of the receiving end voltage, we have to reduce the positiveness. For example, so don't by heart these values. These are some example values I have taken. For example, I am taking Vs is 220 volts and XL is 220 ohms and Q absorbing is 10 and Q delivered is, or otherwise Q absorbed is some 0. Suppose Q delivered is 0. Suppose we are having like this. Then what about QD? QD is 10 minus 0, so it will be having plus 10. Therefore, from the formula whatever we have written there, from that formula, we can write VR1 is equivalent to Vs is 220 minus Vs is 220 into, not Vs, it is QD. QD is 10 into XL is 220 and Vs is 220. So that 220 will be cancelled and 220 minus 10, so that we will get 210 volts. So that we are saying 210 volts is less than that of Vs. So that VR1 is less than Vs. That's what we are having here. Now in this one, QD is plus 10. As it is plus 10, we are getting VR1 is less than that of Vs. If you reduce the positiveness of this one, reducing positiveness means if you are making it as 9, so that 220 minus 9, 211 increased, 220 minus 8, from 10 to 8 I have reduced the positiveness. So 212, 7, 213, 6, 214, 5, 215, like that. Whenever you are reducing the positiveness of the reactive power demand of the load, then automatically the receiving end voltage will be increased. Reducing the positiveness is nothing but increasing the negativeness. So reducing the positiveness is nothing but increasing the negativeness. So here we are having 10 minus 0. So if you are connecting a device which is going to deliver some reactive power of 1 or 2 or 3 or 4, like that, whenever it is continuously increasing, automatically the positiveness of QD will be reduced, so that automatically receiving end voltage will be increased. Remember, very simple concept. but you have to understand this one. Clear? Yeah. Now check here. In this one, to reduce the negativeness or to reduce the positiveness, Q delivered should be increased. So that connect a device which is able to deliver reactive power. Connect a device which supplies or delivers Q. Which supplies or delivers Q. What is that one? That is nothing but a capacitor. Clear? So that we can connect a capacitor to reduce the reactive power. Clear? To reduce the positiveness of the reactive power. Clear? Now, how we can connect the capacitor? In shunt we can connect, in series we can connect. We are having two discussions. So in this class we are going to discuss only about the shunt connection, but actually we are having both. So we'll see, we'll compare both and we'll give finally which is the best one. I'm saying here shunt connection is the best one to improve the voltage here, but whenever we are listening the classes clearly, so that we can give complete discussion about shunt capacitor and series capacitor, and finally we can conclude which is the best one, right? So the final conclusion is the shunt capacitor. So it can be connected in shunt or it can be connected in series. So in this class we are discussing about the shunt connection. Clear? So now we'll connect a shunt capacitor at the load side, right? Now we'll connect a shunt capacitor at the load side. Now check here. So this is the system we are having. Here we are having the load, so which is having a Q demand and receiving end voltage VR2, magnitude, sending end voltage Vs, line reactance JXL. Now here we are connecting a capacitor of QC. We can call it as QCSH, the shunt capacitor value. Shunt capacitor QCSH. Clear? Now the overall reactive port demand, will become, therefore the overall reactive port demand will become QD is equivalent to Q absorbed minus Q delivered of the load, and extra we are having minus QCSH. That's what we are having the total demand. If it is 10, if it is 0, if you are having 1 here, it total become 9, right? If it is 10, if it is 0, if it is 5, total will become 5. Clear? So like that we are reducing the positiveness. Now coming to here, just listen carefully here. What about the receiving end voltage? VR2 is equivalent to Vs minus Qs into XL divided by Vs. In place of Qs, we have to write QD. So it will be Vs minus QD will be Q absorbed minus Q delivered minus QCSH whole divided by Vs into XL. So that by seeing the equation itself, we can say the value of VR2 has been increased. Therefore, we can say the receiving end voltage VR2 is more than that of VR1 compared to the previous case. Compared to the previous case, it has been increased. But still, this VR2 is still less than that of Vs only. We have increased by 1 only, so that it may become 211 or it may become 212. The 212 is still less than that of the sending end voltage, right? Therefore, just listen here. But still, VR2 is less than Vs. VR2 is less than Vs. Now to get VR2 is equivalent to Vs, that is the final condition we need to get VR2 is equivalent to Vs. What we have to do now? We have to make this demand. See here, this demand should be equivalent to 0. QD must be equivalent to 0. So which means that Q absorbed minus Q delivered minus QCSH must be equivalent to 0. Therefore, the value of QCSH is nothing but Q absorbed minus Q delivered. Q absorbed minus Q delivered. If you want to give perfect notations here, right? So this is the old demand, QD old, and this will be QD new, right? This will be QD old and QD new. So that the new QD should be equivalent to 0. So that this is the old. Therefore, QCSH must be equivalent to QD old value. That means the capacitor has to supply the overall demand, the overall reactive power demand of the load. So whenever it is able to supply the overall reactive power demand of the load, so then only it is possible to get the receiving end voltage which is exactly equivalent to the sending end voltage. So that is the conclusion we can write. So when the capacitor supplies overall reactive power demand of the load, then VR is equivalent to Vs. So we can get the receiving end voltage is exactly equivalent to the sending end voltage. Clear? So in this way, the shunt capacitor can improve the voltage and it can supply the reactive power and it can improve the voltage. Therefore, the advantage of shunt capacitor is that it can improve the voltage and it can supply the reactive power to the system. And along with improving the reactive power, it is also improving the power factor. Because the capacitor always improves the power factor of the system, right? Now check here. Initially, we are having a system like this. Suppose the initial active power supplied by the source is PS, the initial reactive power supplied by the source is QD old. Clear? And this is the initial apparent power supplied by the source. Now we are connecting a reactive power or capacitor. That capacitor is reducing the, it is in the reverse direction, right? So it will be QC minus QCSH. So because if you add this one here, so it will be coming in the reverse direction. So it will be QCSH, right? We are adding here, and therefore, so this is the resultant apparent power we are having, right? And this is the resultant reactive power. So suppose if it is Q1 initially, and if it is P1 initially, in the second case we are having Q2. What is the value of Q2? Q2 from Q1 we are subtracting QCSH. So that Q1 minus QCSH. So that is the resultant reactive power, and this is the resultant apparent power, S2, if we are calling it as S1. So it will be S2 and S1. And is there any change in the active power? As we are connecting a pure capacitor, the capacitor never absorbs active power, never delivers active power, so that there is no change in the active power. So that there is no change, P1 is exactly equivalent to P2 in both the cases. Clear? So now if you compare the power factor, initially this is the power factor angle phi 1, and whenever the capacitor is connected, this is the power factor angle phi 2. If you see, phi 2 is less than that of phi 1, therefore cos phi 2 is greater than that of cos phi 1. Cos phi 2 is greater than that of cos phi 1. Clear? So like that we can calculate the power factor, right? And from this one, so from this formula, as Q2 is equivalent to Q1 minus QCSH, so QCSH is equivalent to Q1 minus Q2, Q1 minus Q2. So to calculate Q in terms of the power factor angle, so it is P tan phi. So therefore the value of QCSH is nothing but P tan phi 1 minus P tan phi 2. It will be P into tan phi 1 minus tan phi 2. Tan phi 1 minus tan phi 2. That is the formula to calculate the reactive power supplied by the capacitor. Clear everyone? So this is the discussion what we are having about the shunt capacitor. So now we'll solve a simple problem on this one. Please take it. Yeah. A single source is supplying power to a single load, and the load is operating at 50 kilowatt and 0.5 power factor lagging. If the capacitor is connected to improve the power factor to 0.8 lagging, then the reactive power supplied by the capacitor. Very simple. So just directly we can write the formula here. What is that? The reactive power supplied by the capacitor, QCSH is equivalent to P into tan phi 1 minus tan phi 2. If you remember the formula, where P is 50 kilo into tan phi 1. So cos phi 1 is given 0.5. So tan of cos inverse of 0.5. Tan of cos inverse of 0.5 minus tan of cos inverse of 0.8. That is the second power factor. Tan of cos inverse of 0.8. So if you calculate that one, that will be the resultant reactive power. So let me calculate here. So it will be, let me calculate. So it's a very simple one. So it will be 50 into tan of cos inverse of 0.5, tan of cos inverse of 0.5 minus tan of cos inverse of 0.8. So it will be approximately 84.04 kVAR. That is the reactive power supplied by the capacitor. Very simple. Clear? And you can get the values. Tan of cos inverse of 0.5. What is cos inverse of 0.5? It will be 60 degrees. So tan 60 it will be root 3. So tan of cos inverse of 0.8 it will be 0.75. Right? So it will be, so root 3 minus 1.732 minus 0.75. You can just check here. Cos inverse of 0.5 it will be 60 degrees, right? And cos inverse of 0.8 will be 36.86 degrees. So therefore, so tan of 60 it will be root 3, 1.732 minus tan of cos inverse of 36.86 it will be, or tan of 36.86 it will be 0.75. So 1.73 minus 0.75. So if you take and if you multiply with that one, approximately you will get the perfect answer. Please check it and calculate that one. Clear? So in this way we can calculate. So that is we are having here, and we can take one more problem here. Suppose in the same case, if the power factor, if the capacitor is improving the power factor to unity. In the same problem, if just I am taking the same problem and the capacitor is improving the power factor to unity. Clear? So that what happens? Cos phi 2 will become 0. Right? Or not 0, it will be 1. 1. Therefore, tan phi 2 will become 0. Therefore, QCSH is equivalent to, so P into tan phi 1, that is sufficient. So it will be P into or 50 into 50K into tan of cos inverse of 0.5. Cos inverse of 0.5. So 0.5 will get for cos 60. So it will be tan 60, it will be 50 root 3 kVA. Like that we can calculate. Right, students? So in this way we can solve some simple problems for GENCO, Transco and Discom exams. And this is the discussion about the shunt capacitor. I think it is very clear for you. So in this way we can discuss about the remaining devices also, series capacitor and remaining all the devices. So everything will be very clear for you and you can get more knowledge on the subject, and we will provide more practice questions for you, and we will try to solve almost all the practice questions in the class itself. And so the faculties are giving more extra topics to understand also, right? So that's what we are having today. So thank you for everyone and thank you for attending the class.